Today, we want to discuss about the latest approaches in numerical modeling of nanofluid. Because this is a short course, this is just a 30-minute presentation. We cannot go for details, but just I'm trying to give you a background about what is going on in nanofluid and what the numerical approaches that used in nanofluid modeling. Okay, first of all, we should talk about this topic that what is nanotechnology, okay? First, we should know what is nanotechnology. Nanotechnology is not something, weird or something special. It's just about the sizes. For example, you see the size of an ant is 3 to 7 millimeter. The size of a blood cell is around 7 micrometer. But here, in this part, we are talking about 0.1 nanometer to 100 nanometer. This is the size that we call it nanotechnology, okay? For example, a carbon nanotube size is something near 20 to 50 nanometer, or the water molecule is around 0.1 nanometer. So it's just about the sizes. A technology about very tiny and small sizes, between 0.1 nanometer and 100 nanometer. But if we think about this range of the size, from 100 nanometer to 100 micrometer, then we are going to micro technology or micro size that we need to talk about it later, okay? So now nanotechnology just is about the size. Okay, the next thing that I want to talk with you, these topics and this presentation is more about the heat transfer and fluid flow, so I hope you have some background on it. Otherwise, I give you some initial data. The thing is that for heat transfer system, we need some fluid. The common fluid that we use normally in this system are normally our water or oil, ethylene glycol, or something like that. This material have a low thermal conductivity. If you know, thermal conductivity is the capability of a solid or fluid or gas that can transfer the heat from the hot part to the cold area, okay? Just it's the capability of the material to transfer the heat, okay? For example, normal heat transfer fluid, this value is very low. It's normally less than 1 watt per meter Kelvin, okay? But for solid, like ceramics, this value is around 100, means 100 times more than fluid. And for metal like copper, this value is around 400, which is much, much bigger than the fluid. And for some material like carbon-based graphene platelet or carbon nanotube, this value is between 3,000 to 5,000 bigger than the normal fluid that we use in our system. So an idea comes to our mind, how we can use the capability of this solid inside this fluid to enhance the capability of this fluid to transfer the heat better. In the scientific word, we call it how we can use this material, the solid material inside this fluid material to enhance the thermal conductivity and heat transfer. This is the scientific word we use in mechanical engineering. And this idea have been proposed around more than 130 years ago, that we come slice this solid particle to a small parts and add it with some physical or chemical method to the base fluid. Therefore, the thermal conductivity of the fluid going up. In that time, and by the technology in that time, they could just, cut the solid particle to micro size, okay, to the micro size. When they add the microscopic particle to the water or other fluids, then they saw there are many problems that happen. Of course, the heat transfer going up, but this particle can clog the pipe, If there is a pipe, they can clog the pipe. Or they can sediment inside the pipe. Means going down, settling down, and make the sedimentation. That during the time, the heat transfer become worse, and also the pipe again will be clogged, okay? So the idea was good, but the work doesn't work for a human. Even many physicists like Einstein and many other people work on it, but it doesn't work until 1995, a report was released from US Army that a researcher with the name of S.U.S. Choi introduced a new idea that was the same idea of the micro-size fluid, but he could small the sizes to nano size. He could go down and make the smaller and more tiny particle in the nano size, okay? So he could make the particle in the nano size, add it with some method to the fluid, and then he could make the nanofluid. So nanofluid is a base fluid, a fluid that we use in our system that some nanoparticle has been added to this base fluid. And this adding is not just a simple just adding the particle, no. If you just put the nanoparticle to the base fluid, it will go in settling down, okay? Or make the agglomeration, means the particle are go and become bound together. And this is not the thing we are looking for. So by using some physical methods or chemical methods, we can make a stable homogeneous fluid that we call it nanofluid. So now we know that what is nanofluid and we know how they make it. This topic can be continued to talk about it, but because today we are working on the numerical methods, so I just close the topic here. And maybe in the future, in another talk, we can talk about how these nanofluids can be prepared and how their thermophysical properties and other properties can be measured. Okay. Here I have a picture that I would like to show you about the application of nanofluid. For me, as a mechanical engineer, the nanofluid application is in heat transfer system like that, or in energy harvesting system. But for other knowledges, for example, like hyperthermia therapy or cosmetic or anti-infection therapy or defect sensor, still we can see the application of nanofluid. So it shows that this nanofluid is a multidisciplinary area of research. And during the years, you can see here, this is the number of articles that published in Scopus journal during the year. You can see the attention of researchers have become more and more to this topic. For example, between 1995 to 2004, in 10 years, just 98 papers published on nanofluid. But in 2020, more than 3,800 papers have been published on nanofluid. It shows that the nanofluid is a hot topic in the world, especially in Asia, Africa, and Europe. Okay, now I want to change the topic. Now we know the basic of nanofluid, nanotechnology, and everything. And now I want to talk about numerical method that used for this modeling of nanofluid. In the measure way, there are three different ways. One is single phase method, multi-phase or two-phase method, and the other method that we call it other. Here I just wrote LBM, but there are many others that we can talk about. The single phase method can be divided to two parts, dispersion and conventional. That for conventional, if you know a bit about the numerical modeling, you know this method, like finite volume method, finite element method, finite difference method, and many more. For two-phase, when we divide the modeling to two parts, it becomes Eulerian Lagrangian or Eulerian. That Eulerian can be divided to three parts of mixture model, Eulerian model, or volume of fluid. And of course, we have other methods. Okay, go and talk about each of them. Single phase method is the first method that have been used in the world to model the nanofluid fluid in heat transfer system. Okay, and it's a very easy method. You know, when you want to model a fluid inside any system. For example, you want to see how wind go around your house, or you want to see how the river flows, or anything, any fluid. Normally, we solve the Navier-Stokes equation. They are the basic equation that govern on all the fluid flow in the world, okay? For single-phase nanofluid modeling, we use this Navier-Stokes equation, just change the thermophysical property of the fluid by the thermophysical property of nanofluid. For example, we use the same equation for water, but instead of putting the density or viscosity or thermal expansion of water, I use these values for nanofluid. This is the easiest thing. We have the code, we have the software in the world, just need to change the thermophysical property. It's like this. It's easy. Okay? This is the most used method in the world for modeling of nanofluid. But here we have a problem that arose in 2012 and after that. It's about how we calculate this thermophysical property of nanofluid. How? Here I have some part of a review paper that have been cited more than 200 times. There are, you can see, some formula here to estimate the viscosity of nanofluid. For example, one of the very famous formula that used for calculating the viscosity of nanofluid is Einstein model, which was proposed in 1908, or the Brinkmann model that was proposed in 1952, or this model in 1959, or Frankel model in 1967. Just come and think together about it. Nanofluid was introduced in 1995 by S.U.S. Choi. But some people use the Einstein model or the model from 1950 or 1960 for such fluid. Do you think it worked properly? I don't think so. Many other people also don't think so. This formula have been developed for micro-sized fluid. I told you, more than around 150 years ago, researcher could make the micro-sized fluid or microfluid. Means they could, you know, divide it and chop the solid in the micro size and add it to the fluid. That had many problems. Okay. This formula is for micro size, not for nano size. But unfortunately, many people in their researches, especially before 2012, 2013, have used this formula for nanofluid. That's the thing. The single phase modeling is okay. We don't have any problem with it. But most of the paper published on single phase are wrong because they have used the wrong and false thermophysical properties formula. So you ask me, Reza, what we should do to do a correct modeling? Is the thing. If you want to use the single phase modeling, then please use the experimental data that some other people from material science or physics have been measured and reported in the paper. Then maybe they have done some regression or data, or you can do the regression by yourself, by any software you like, and got such formula. That, you know, this formula is, for example, this formula is example just work for SiO2 transformer oil and up to just 1% of the nano, just for this. For this specific material and for this specific volume of fraction, not for others. Then you ask me, Reza, why are you talking about the volume fraction? What is the importance of volume fraction? You know, volume fraction of nanoparticle means the amount of nanoparticle you add to base fluid. More volume fraction means adding more particle to the base fluid, okay? In the Einstein or other formula you can see here, they just consider the effect of phi. Phi is, I told you, is volume fraction. But they did not consider the effect of temperature or the effect of the size of the particle, because I told you this formula is for micro size. And I'm telling you, this wrong formula is not just about viscosity, it's about thermal conductivity, it's about density and others. They did not consider the effect of different parameters, you know. But the experimental work of material scientists showed us, for example, if we have a nanofluid here, and we keep the size of the particle and amount of the particle inside the fluid constant, by increasing the temperature, okay, the viscosity of the nanofluid going down, but the temperature, the thermal conductivity going up, okay? But for example, here, If we have a nanofluid and keep the temperature and volume fraction constant and just increase the size of the nanoparticle, then viscosity and thermal conductivity both going down. And something in contrast with that happens when we increase the volume fraction. So it means that all of these three parameters are very important in the thermophysical property of nanofluid. And when people want to use the single phase modeling for nanofluid, they have used the formula for thermophysical properties that consider all of these three parameters: temperature, volume fraction that I told you that it's the amount of nanoparticle you add to the base fluid, and the size of the particle diameter. If we consider these three parameters correctly in our formula, then our modeling is correct. Otherwise, our modeling is completely rubbish. Okay, the other famous modeling for single phase is dispersion model. I don't want to talk about formula because we don't have time. It means that some scientists have came and modified the Navier-Stokes equation by considering some small chaos in velocity and temperature magnitude. Because it is a very short talk, I don't go for its details, but if you want, you can call me and we can discuss about it. It gives better result compared to the previous model, but its coding is really hard, of course, harder than single phase, and there is no commercial software that have this formula. So the published paper on this model is not much, it's just few papers. Now I want to talk about two-phase approaches that I told you. There are two famous models, two famous point of view. One is Eulerian, and the other was Eulerian Lagrangian. That this is just 2 point of view how do you consider your fluid. It's from fluid mechanics course in undergraduate for engineers. And if I want to give you a brief idea about it, it takes you that, for example, these two ideas. We have a fluid and we have some particle, okay? You can consider that there are single continuum media, means they are go together. It means that, for example, particles have been settled on the molecules of fluid and go together, okay? They are go together. This is one point of view. The other point of view is that you have fluid, you have particle. The fluid is a continuum, it's go. And for example, you inject the particle inside it. Okay, this other view. So it depends on you, how do you want to see these two? Based on what you think about it, what is your point of view, we have two different approaches. Okay, for Eulerian Lagrangian model, which is this one, there is just one model that we can use for nanofluid modeling. They call it Eulerian Lagrangian, or they call it DPM, discrete phase model. As I told you, for this one, we consider that the fluid is just flows as a continuum media, okay, just flows, and we inject the particle inside it. This is the point of view that this modeling uses. This modeling, this is the formula of the modeling, is very precise model. It's very good. Can be used for a specific type of modeling like erosion, corrosion, or for falling and mitigation. And it's really accurate model, okay, because the point of view is really accurate, but it has some limitation, actually 2 or 3 limitations. The first limitation, which actually is about the exist computer, is that you say that we inject particle inside the fluid and we track each particle. It's not just, of course, you inject the particle. This is your point of view. But you want to track each of these particles. So by present computer, you can just inject up to maximum 1 million particles inside your fluid. So if you're you have more particle, then this model will not work for you. It's just about the limitation of the software and the model. The second and third problem again is about computer. First thing is This model is very time consuming, takes a lot of time from you. And the third thing is, again, is about the limitation of computer. You need to have a high performance computer to do this modeling. Otherwise, with normal computer, always you are facing with crashing your computer or burning your hard disk, problem in RAM and many of the stuff like that. But it's really very good model. This is one of the modeling I have done in 2015. If that was erosion corrosion modeling inside a real size bin. This is the application of this modeling. Okay. Now we go to Eulerian point of view, that compared to Eulerian Lagrangian takes less time and needs, higher quality computer, means cheaper computer. It has three different models. The first model is VOF, volume of fluid. I want to tell you, using VOF for modeling the nanofluid is completely rubbish. So if you see and read an ISI paper that use the VOF model to model nanofluid flow inside the normal pipe or something like that, I'm telling you, this is completely wrong. This is completely incorrect. But unfortunately, there are many papers published in the world that use this model, because this model should be used to model the interface between fluid phases. For example, there's water in a dam, and the water, has the interface with air, okay? So you want to do that modeling, of course, you use VOF because it's free surface, or you have a bubble inside the fluid that is one grew, and pop the bubble. Of course, you use this model. But this model should not be used for nanofluid modeling. That's the reason, is that the size of the nanoparticle is much smaller than the computational scene. And these particles are displaced in the base fluid. So VOF model cannot track this particle, cannot consider this particle. So please do not use this model for nanofluid modeling. Second method is mixture method, okay? It's from the computational time, it's still time consuming, but it's much better than DPM and some other model that I will tell you later. The result of this model is very precise, but it has, again, limitation. The most limitation of this model is that you just can model the nanoparticles that are spherical and in the uniform size. So if you see a paper that have used a non-spherical particle, nanoparticle like carbon nanotube, which is tube, or graphene nanoplatelet that are plate, okay? If they use mixture model, please consider this fact that this modeling is completely wrong, because this model is just for spherical model. Many of the commercial software like Fluent or COMSOL Multiphysics have used this formulation to model the mixture, and most of the paper use this modeling just without any modification. But because we don't have time, I don't want to go to details, but if you read this PowerPoint later or call me, we can talk about it, that this formula, the old formula that used in this commercial software, does not work for nanofluid. They have written and developed for micro-sized fluid, not for nanofluid. So this formula should be corrected. Otherwise, they give you wrong result. And of course, I have corrected the formula and published them. So if you want, you can go to the literature, some of my paper, and you see how I have corrected. It's not big deal. You can very easily correct the software like Fluent or COMSOL Multiphysics. It's easy. But the difference between the result is really considerable. And the last two-phase model is Eulerian model. It's really complex. It's really time-consuming. It can be used for a big range of volume fraction. It gives you some specific result that you cannot get by the other model. Some, specific, the outcomes that you cannot get by other models. And it's very good to use it for the problem that you use also with VOF, like bubbly flows or flow bed or something like that. But it's really time consuming. Again, commercial software like Fluent, like Console have this model, you can use it. But again, I could prove that these formula are not correct for using for nanofluid. They have been developed for microfluid, and therefore you have to correct the formula inside the software, or you have developed your own code. Otherwise, your modeling is completely wrong. Again, here we have the corrected formula that I have done it by myself, and you can find them and their details in the literature. All in all, by reading the literature, you can find that the mixture model gives the best result and the less effort compared to other two-phase modeling. So for two-phase modeling, the mixture is the best. And here there are many other approaches. We call them other approaches that some paper publish on it. Some say hey, it's better than two-phase, some say better than single-phase, but there are not much work on it. The most famous one is Lattice-Boltzmann method. Bongiorno method that have been developed by the Professor Giuseppe Bongiorno in MIT. That is the single phase, for example, modeling by considering Brownian diffusion and thermophoresis, which are very important in nanofluid modeling. So the result of this modeling is much better than single phase modeling. And many other different methods like molecular dynamic, SPH, OHAM, HAM, CVFEM, or meshless method like Petrov-Galergin, finite pod methods, and many others that normally used by mathematician, not by engineer. Engineer normally use the single phase or two phase that I told you in details. Okay, because we don't have much time, I go for conclusion. The first thing we should consider for our modeling, Brownian motion and thermophoresis are two forces that are very important in nanofluid modeling that most of the single phase model do not consider them. So please remind this in your mind. The second thing is that normally multi-phase modeling give you better result compared to single phase because they consider Brownian and thermophoresis, okay? And between all the multi-phase models, two-phase mixture model is the best model that you can use. And the last thing that should be considered, unfortunately, in most of the publication, you can see they say, okay, we have used a particle, we compare two particles. This one have a higher, for example, thermal conductivity, so it gives you better heat transfer. It always not like that. Always is not like that. For example, if you consider and compare SiO2 with this amount of thermal conductivity, with Al2O3, that the thermal conductivity is 40, you consider 40 with 1.4, okay? You may think, okay, 40 is bigger than 1.4, so it gives you better transfer, but I'm telling you, no, it's not ever like that. Because the density of the SiO2 is much, much less than Al2O3, alumina. It gives you a higher velocity, and therefore, in all, the heat transfer of SiO2 is better than Al2O3. But unfortunately, most of the researchers doesn't know about it, okay? So they say, okay, higher thermal conductivity, higher heat transfer. No, it's not like that. Please consider that. And for future work, I want to give you some suggestions that can be considered to writing the grants or consider for publish the article. There are the topics that are not work a lot on it, on numerical modeling that can be published in the future. The first thing is that most of the nanoparticles that have been studied in the world are this type of nanoparticle: alumina, copper oxide, titanium oxide, silicon oxide, or carbon nanotube. So I want to give you this suggestion: go and work on new shape and new type of nanoparticle as a part of your nanofluid. The second thing is that most of the paper published on CFD modeling of nanofluid have been used the finite volume method and normally Fluent software. So please go for other methods, use them, and enhance your publication. The third thing is that most of experimental and numerical work on nanofluid have been done on laminar or turbulent modeling and regime, turbulent or laminar regime. You know, for experimental work, it's really hard to, you know, capture the data in transition. Same thing for numerical modeling. So not much work have been done on transition. So please, if you want to do a novel work, go and model the transition fluid. Some other idea is that, for example, come and do not use two-dimensional modeling because most of the work in nanofluid are 2D. Please go for 3D and add, for example, some vibration to the fluid. Or for particle sedimentation, erosion, corrosion, solidification and melting, or pool boiling of nanofluid, there are not much work have been done in the world yet. In each of these topics, if you search the numerical modeling, there is less than 10 papers. I'm telling you, I have searched again last week. It is less than 10 papers in each of these topics in the world that have been published on nanofluid. So still they are fresh. You can write your grant on it. You can write your student proposal on it and publish in reputed journal and enhance the knowledge of the world by working on these topics. Of course, still you still can work on new type of nanofluid like hybrid nanofluid or nanorefrigerant. There is still not much work on them, and you can work on it to get newer result and newer paper with new idea. Here is my references. And if you need any information, if you have any question or need collaboration, please contact me on my email address that you can see here, or my phone that you can reach directly, or through WhatsApp. You can reach me, and it will be my pleasure to talk about it with you. Thank you so much for consideration. I'm ready for your question. Thank you.